1 minute ago, seismic instruments across Sicily registered something unprecedented. Synchronized structural failure across a 25-kilometer fault zone appeared in Mount Etna's data for the first time in recorded history. Not a quake, not an eruption. A catastrophic slow-motion collapse has begun accelerating. The same process last seen 8,000 years ago is repeating its precursor patterns. What is fueling this crisis, and who is truly at risk now? Could 130 million lives across the Mediterranean be threatened by a mountain most people have never heard of, sliding into the sea? 8 millennia ago, Etna's eastern flank failed catastrophically. Between 6 and 8 cubic kilometers of volcanic rock, approximately 15 billion tons of material, slid into the Ionian Sea in a single event. The result was the largest volcanic tsunami in known Mediterranean history. Waves reached heights of 30 to 40 meters. They traveled at speeds approaching 700 kilometers per hour. Destruction spread from Sicily to Turkey in a matter of hours. Entire Bronze Age coastal settlements vanished beneath the surge. The village of Atlat Yam in present-day Israel was abandoned suddenly, its inhabitants fleeing with gutted fish left to rot on tables. Sediment cores from the Mediterranean seafloor confirm the scale of devastation, with displaced material tracked from the Ionian Sea all the way to the Sidra Gulf off Libya. This collapse is now repeating its precursor patterns. The volcano towers 3,357 meters above sea level. Its mass exceeds 500 billion tons. Unlike stable volcanic systems elsewhere, Etna rests on a foundation that was never meant to bear such weight. Beneath the mountain lies a layer of weak sediments and ancient seafloor deposits. Clay and gypsum formations spread across kilometers, compressed by the immense pressure from above. This creates a rare global phenomenon that scientists describe with clinical precision: a giant volcano slowly sliding into the sea under its own weight. The mechanics are unforgiving. Etna's base sits at the edge of the European continental plate where it meets the African plate. The sediments beneath it, deposited millions of years ago when this region was submerged, act as a slippery detachment layer. Gravity pulls relentlessly downward and seaward. But the real danger was hiding underwater. For decades, scientists monitored eruptions and lava flows from the summit. The surface activity seemed to be the main threat. Slow creep of 2 to 4 centimeters per year was documented onshore, but dismissed as harmless, gradual spreading. The prevailing scientific consensus held that magma pressure drove flank movement. Gravitational forces were proposed, but considered secondary. The underwater portion of the volcano where the most critical instability signs were developing remained largely invisible to monitoring systems. This was the blind spot that persisted for generations. Land-based GPS stations tracked surface displacement with precision, but couldn't capture what was happening beneath the waves. Researchers focused on predicting eruptions, building models around magma chamber dynamics and gas emissions. The slow structural failure occurring kilometers offshore escaped comprehensive analysis. What came next shocked even the scientists. On December 26, 2018, at 2:19 UTC, the largest instrumental earthquake ever recorded at Etna struck the southeastern flank. The magnitude 4.9 event ruptured the Fiandaca fault with exceptional violence for such a moderate size. The hypocenter sat at just 300 meters depth. Surface faulting extended for approximately 8 kilometers. Right lateral slip with oblique extension created fractures that tore through villages between Flery and Penisi. Maximum displacement reached 35 centimeters in places. The earthquake damaged over 600 buildings and displaced more than 1,100 people. The intensity reached 8 on the European macroseismic scale along a narrow strip astride the fault. What stunned geologists was not the shaking, but what the rupture revealed. This was structural tearing, Not typical volcanic behavior. Field teams mapping the surface breaks discovered something unprecedented. The Fiandaca fault had activated its entire 13-kilometer length, mirroring the last complete rupture in 1894. But detailed analysis of the fracture patterns showed a complexity that went beyond simple earthquake mechanics. The fault zone fabric revealed multiple stress fields acting simultaneously. Contractional and extensional features appeared side by side, each responding to different forces. This was the signature of a mountain being pulled apart by competing dynamics. Seismological data confirmed the fault's unusual behavior. The event generated minimal aftershocks, an extremely rare circumstance for magnitude 4.9 earthquakes. The time domain moment tensor solution showed pure strike-slip faulting along a subvertical plane. But the real breakthrough came from examining what happened below the waterline. Between April 2016 and July 2017, researchers deployed the first long-term seafloor displacement monitoring campaign at Etna. 5 autonomous transponders were positioned across the offshore extension of fault systems related to flank kinematics. The instrument sat approximately 40 kilometers from the volcano's central crater. For months, the transponders remained at stable positions. Then, in May 2017, during an 8-day period, they recorded a slip of more than 4 centimeters. Displacement on land peaked at approximately 4 centimeters at the coast, with deformation increasing away from the magmatic system. The data revealed 11 distinct slow slip events over the monitoring period. These weren't gradual movements, they occurred in sudden bursts ranging from 2 to 67 days duration, with irregular recurrence averaging 348 days. Each event showed the eastern flank detaching incrementally from the rest of the mountain. The pattern confirmed what scientists had suspected but couldn't prove. The bulk of Etna's continuous deformation is driven by gravity while being further destabilized by magma dynamics. The submarine portion of the volcano was sliding independently, responding to gravitational pull rather than volcanic pressure. Frequency and intensity were rapidly increasing, and the signs were already spreading. Analysis in 2024 and 2025 revealed accelerating trends. High-precision creep meters installed across the main slip zone detected short bursts of motion during quiet periods. One instrument above the Fiandaca sector recorded a sudden acceleration in February with no surface expression and no felt shaking. Field excavations confirmed faint shifts in shallow soil layers. The displacement wasn't enough to threaten infrastructure immediately, but it proved the flank forces were continuously active. Artificial intelligence mapping of thousands of microquakes uncovered a newly identified ring fault encircling the caldera. These swarms cluster along structures that could focus future earthquakes and amplify risk. The most alarming data came from comparing historical movement rates with current trends. Paleoseismological studies along the Fiandaca fault revealed throw rates increasing from 1.4 millimeters per year during the 15,000 to 3,900 year interval to 10 millimeters per year since the late Middle Ages. The mountain's instability is growing exponentially. But this was only the first warning. Beneath Etna's eastern flank lies the mechanism that could trigger catastrophic collapse. Seismic imaging reveals the eastern section sits atop layers of clay, gypsum, and ancient fault plains compressed under immense weight. These materials act as a lubricant under pressure. As Etna's mass presses down, the mountain spreads outward. The detachment layer allows the entire southeastern slope to slide seaward along a basal plain that extends kilometers beneath the surface. Scientists describe it as a nested pattern of fault-associated detachments.
The geometry is deeply unsettling. Multiple subsectors exist within the unstable flank, each bounded by intervening faults. These sectors can move independently or synchronized during large slip events. Research comparing Etna to other unstable volcanoes worldwide reveals troubling parallels. Kilauea and Hawaii experiences similar slow slip events along its submarine southern flank. The events there occur along an offshore basal décalement with durations of several hours to 2 days. At Etna, the timescales are longer, but the physics identical. Gravitational spreading over weak sedimentary layers creates conditions for sudden failure. When enough strain accumulates, the mountain can detach along the lubricated boundary. The warning from experts is unambiguous. We cannot exclude flank movement evolving into catastrophic collapse. This implies Etna's instability poses a far greater hazard than previously thought. International research teams have modeled a collapse scenario equivalent to the event 8,000 years ago. They used sonar surveys of displaced seafloor sediment to constrain the volume and velocity of the ancient landslide. Computer simulations then calculated tsunami propagation across the Mediterranean basin. The results are catastrophic. Within 10 to 20 minutes, Sicily's Ionian coast would be obliterated by waves 30 to 50 meters high. Coastal towns like Osraele, Catania, and Taormina sit directly in the impact zone. Between 30 and 45 minutes after collapse, waves 15 to 25 meters tall would strike Calabria and the Aeolian Islands. Within 1 hour, Malta and Greek Ionian Islands would face surges 12 to 20 meters high. The tsunami would then spread across the entire Mediterranean basin over subsequent hours. Conservative casualty estimates suggest 1 to 2 million deaths in the first 2 hours. The wave speeds approach 450 kilometers per hour in deep water. As the tsunami reaches shallow continental shelves, it compresses and amplifies. The eastern Mediterranean coastline offers little natural protection. Bays and river mouths would funnel water inland. Cities built on low-lying coastal plains would experience complete inundation. The models show the surge could penetrate up to 2 kilometers inland in some locations. Historical precedent exists, but on a smaller scale. In December 2002, a chunk of Stromboli volcano collapsed into the Tyrrhenian Sea, generating a 10-meter tsunami. It snapped moorings of oil tankers in Milazzo Harbor 100 kilometers away, but caused minimal casualties because the event occurred in daylight with witnesses. A collapse of Etna's eastern flank would be 100 times larger. But the ground had one more secret. Modern society is exponentially more vulnerable than ancient civilizations. Over 130 million people now live along Mediterranean coastlines that were devastated 8,000 years ago. Major cities like Naples, Palermo, Valletta, Athens, and Patras were built without consideration of volcanic tsunami hazards. Population density in the impact zone has increased by orders of magnitude. Critical infrastructure crowds the shoreline. Ports, power stations, hospitals, airports, and chemical facilities sit within the projected inundation zones. Evacuation plans designed for earthquake or traditional tsunami scenarios are useless for events with minutes of warning. The 2004 Indian Ocean tsunami killed over 180,000 people, despite hours of potential warning time in some locations. An Etna collapse would provide far less notice. Coastal communities can't be evacuated in 10 minutes. Our emergency services couldn't reach most areas before the first wave hit. Bridges and roads would be overwhelmed by panic traffic. The economic disruption would extend globally. Mediterranean shipping routes carry a substantial portion of world trade. Destruction of port facilities across multiple countries would create supply chain collapse. Tourism industries throughout the region would face complete shutdown. Insurance models haven't priced this risk. Governments haven't prepared for it. The general population remains largely unaware that the threat exists. What came next shocked even the scientists. Etna is not alone. Many volcanoes worldwide share the same gravitational instability. The Canary Islands contain Cumbre Vieja, where a massive collapse could trigger a transatlantic tsunami, potentially affecting North and South America. Hawaii's underwater flanks show evidence of gigantic ancient landslides. The Nuuanu debris field off Oahu extends 200 kilometers across the ocean floor. Similar features exist around volcanic islands in the Lesser Antilles. Etna may be the first major coastal volcano we observe collapsing in real time, but the hazard is global and the warning signs are multiplying. Research published in recent years reveals that the threat has been systematically underestimated.
The challenge isn't identifying the risk. Scientists understand the mechanics clearly. The failure lies in translating that knowledge into protective action. And the signs were already spreading. Italy's tsunami warning system detects earthquakes through seismometers. It triggers alerts when undersea quakes of sufficient magnitude occur. But this system cannot detect flank collapses that happen without seismic precursors, or with signals too small to distinguish from background activity. Malta has no volcanic tsunami emergency plan whatsoever. The island sits directly in the path of waves that would arrive within 1 hour of Etna's collapse. Government disaster protocols focus on earthquake and weather threats. United Nations disaster risk documents rank volcanic tsunamis as low probability, despite mounting evidence. The hazard doesn't appear in most national risk assessments across the Mediterranean. Funding for submarine volcano monitoring remains minimal compared to traditional seismic networks. The disconnect between scientific understanding and policy response is stark. Researchers publishing in Science Advances and Geophysical Research Letters document accelerating instability with precision. Those findings don't translate into evacuation planning, infrastructure hardening, or public education campaigns. Even the scientific community debates details. Some tsunami modelers argue the Italian simulations use unrealistic initial conditions, including impossibly fast underwater velocities for the collapse. Others counter that even conservative estimates produce catastrophic results. The uncertainty doesn't reduce the threat, it obscures the urgency. The data now shows a massive slab of volcanic rock moved 4 centimeters in just 8 days. Structural failure is accelerating beyond all recorded history. The seafloor geodetic data captured movement occurring in sudden episodic bursts rather than gradual creep. Etna is entering the same destabilization phase that preceded the ancient collapse 8,000 years ago. Multiple independent datasets point to the same conclusion. Throw rates along boundary faults are increasing. Slow slip events are occurring more frequently. The shallow gravitational instability extends far into the submarine environment. The offshore portion of the unstable flank encompasses a much larger area than visible from land. Microquake patterns reveal stress distribution within the mountain. The ancient Valle del Bove depression on Etna's eastern flank marks where the previous collapse occurred. The walls of this valley have suffered subsequent failures on numerous occasions. The strata exposed there provide a geological record of catastrophic events stretching back thousands of years. Scientists cannot predict if or when the next collapse will happen. Geologic's timescales don't align with human planning horizons. Etna is 500,000 years old, and catastrophic events may be separated by millennia. But every data point suggests the volcano is primed. The question is not whether the eastern flank could fail, but what happens before it does. Will monitoring networks capture the final precursors? Will authorities order evacuations based on ambiguous signals? Or will 130 million people wake up one morning to sirens they don't understand? The forces beneath Mount Etna don't respond to human timelines. Gravity pulls continuously. Magma pressure fluctuates with eruptive cycles. The detachment layer weakens incrementally under unrelenting stress. Somewhere beneath the Ionian Sea, on a plain of clay and ancient sediment, the eastern flank of Europe's most active volcano continues its slide toward catastrophic failure. The instruments watch, the scientists record, and the Mediterranean coastline waits.